I am thrilled to be here today to share our latest research on learning to remove wrinkled transparent film with polarized prior. This work is a collaborative effort between the Hong Kong University of Science and Technology, Guangzhou, Smartmore Corporation, the Chinese University of Hong Kong, and Zhejiang University. In the realm of industrial applications, deep learning-based models have proven instrumental for tasks like defect detection and code recognition. These models, while effective, are not without their limitations. One significant challenge arises from their insufficient robustness against various perturbations, such as those caused by transparent films. These films, often used to protect materials or products during manufacturing, can interfere significantly with automated processes. For example, they can obscure text or codes, leading to failures in tasks like optical character recognition, OCR, and barcode reading, as illustrated in this figure. In this paper, we introduce a new problem called film removal, FR, which aims to remove the interference of wrinkled transparent films and reconstruct the original information under films for industrial recognition systems. In tackling the challenge of film removal, we have devised a comprehensive model that breaks down the imaging of a wrinkled transparent film into two primary components: the specular highlight, denoted as IH, and the diffuse reflection from the materials underneath, denoted as IMD. The specular highlight IH represents the light directly reflected from the film's surface, which often masks the critical details beneath. The diffuse reflection IMD, however, is what we aim to recover. It represents the light that penetrates the film and interacts with the underlying materials. To enhance the robustness of our approach, we further dissect the diffuse reflection into two parts: the original component IM, which is the true appearance of the underlying material, and the various degradations IMD-IM introduced by the film's properties. Our primary goal is to decouple these two components, the specular highlights and the film-induced degradations, to reconstruct the original, unobstructed view of the underlying materials. This reconstruction is crucial for ensuring the accuracy of industrial downstream models, which rely on clear, unimpeded visual information. Based on this model, our whole framework is based on an end-to-end reconstruction network for decoupling these two parts. Before that, to support the network for decoupling IH, we estimate a polarized prior for locating the highlight regions. To effectively tackle the challenge of decoupling the specular reflections from images, identifying the highlight regions on the surface of wrinkled films is crucial. These regions, however, are notoriously difficult to predict due to the variability in imaging conditions. To address this, we harness the properties of polarized light guided by Fresnel's theory. According to the theory, the specular reflection from optically active materials is predominantly elliptically polarized. This characteristic varies with the angle of polarization orientation, whereas other light components remain relatively constant. Utilizing this principle, we develop polarized prior P, which is defined as the optimized image I with the minimized specular highlight IH, as shown in equation 8. P equals IM plus ID plus minimal IH. Further refining our model, equation describes how we can express IH using the angle variable theta from 0 to 2 pi. IH equals IP, theta, equals Imax, cosine theta square, plus I min sine theta square. In practice, we use a set of input images captured at different polarization angles, 0 degrees, 45 degrees, 90 degrees, and 135 degree, to compute the maximum and minimum intensity components, Imax and Imin, using the Stokes parameters. This allows us to estimate pixel-wise optimal values through a learning-based network, producing an angle map. Additionally, we incorporate two crucial physics statistics: the angle of polarization, AOP, and the degree of polarization, DOP. AOP helps us understand the surface normals, aiding in differentiating the object's structure from the film. Meanwhile, DOP measures the intensity of the polarized light, enabling our network to more accurately leverage this information for specular highlight estimation. To recover the image, we set a reconstruction network FR to decouple both ID and IH with P. We have also built an optical pipeline for capturing the dataset in the industrial environment. As objects traverse the objective pipeline, the polarizing camera captures images continuously. Subsequently, the acquired data is sent to the monitor for pre-processing. To build a diverse and robust dataset, we follow the rules in industrial manufacturing. Current industrial pipeline includes 315 dynamic industrial scenarios, which can be categorized into 3 types: QR codes, text, and products. To enhance the diversity, we have different films with diverse real properties, coverage areas, film thicknesses, and levels of wrinkling. The film exhibits significant variability across each scenario. On the other hand, to ensure the stability of the industrial imaging pipeline, we maintained a consistent intensity level for the industrial light source and fixed the distance between the camera and the object flow. This helps to minimize the influence of errors external to the industrial system. The quantitative results are shown in Table 1. In the last column of Table 1, mu is the mean value, and sigma is the variance of the 10-fold performance. These experimental results show the average PSNR is 36.48 and the average SSIM is 0.9824, and the results demonstrate the high quality of our reconstructed images. In addition, the variance of PSNR and SSIM are 0.57 and 1.23 by 10⁻⁵, respectively, and this proves the proposed algorithm is stable and robust. To evaluate the reconstruction performance of the algorithm in a qualitative way, we show some visual results. To evaluate the effectiveness of our solution in such settings, we conduct 2 tests on 2 downstream tasks: QR code reading and text optical character recognition, text OCR. These tasks are particularly relevant as they require access to raw information, which provides a rigorous test of the effectiveness of our algorithms in industrial scenarios. We conduct ablation studies, which mainly validate the effectiveness of our proposed polarization dataset and one crucial component in our framework. To ensure that the experimental settings are consistent, we perform 10-fold cross-validation for the ablation experiments as well and draw 2 box plots for further analysis. With the support of polarized information, the quantitative performance has a considerable decrease. Also, the performance of the network is limited by the lack of guidance information, so it cannot remove all degradation. Besides, removing the polarization information will induce artifacts in highlight regions. Thanks for your listening. If you want to get more details, you can contact me or visit our project page.